All right, so thanks so much everyone for coming. My name's Daniel Satanaika. I'm a developer advocate on the TensorFlow team at Google. And I've been working a lot with embedded ML over the last year, and it's really the most exciting thing in technology that I've come across in my career. It's super exciting to see how this community is growing as well. And at Google, we're doing as much as we can to support the community and help foster its growth. And part of that is working with some other companies to organize this meetup. And so some of you may have been to our meetups before. For others, it might be your first time. But thank you so much for being here, and I hope you have a great evening. I'm going to hand over to Ravi, who's going to do some more introduction of the tinyML meetup and the tinyML organization. And then we'll hear from our speakers. So thank you very much.
Can everyone hear me? All right, thanks, Daniel, and thanks for hosting. All right, welcome everyone to the Bay Area tinyML meetup. And this is our third meetup since we started back in June. We've been constantly growing, as we talk about right now. For those who are unfamiliar with what tinyML tinyML is anything covering machine learning at the edge in embedded type instantiations with consuming a power of 1 milliwatt or less. So this could be for computer vision applications, audio, sensor processing, anything of that sort. And there's a growing revolution in people working on extremely low power machine learning as deep learning kind of scales up into very, very high power, like nuclear reactor level power consumptions. There's a big revolution brewing in the tiny side of things as well. So the tinyML summit was first started in March of this year by Pete Warden at Google and Evgeny Gusev at Qualcomm and a few others. And just to keep the momentum going from the annual summit, we have these meetup series that's going every month. So what started off in the Bay Area, we've now spread to tinyML Austin. So Arpit Shah from Ambic and Manar El Chamas from Mythic are actually hosting a meetup right now in Austin. So we can all just wave, hi Austin, and they can see us. So they'll be following along. They had a local talk just before this, and they'll now be watching us over here. And as we grow, we expect that, and this is our first time live streaming. Hopefully it all goes through without any issues. So the idea is that we'll keep growing to various locations, and people can even watch at home. So a new volunteer, I don't think he's here today, but Manu Rastogi, from a machine learning scientist from HP Labs, joined our Bay Area tinyML meetup organization. So welcome, Manu. Future meetups, we already have a lineup of meetups coming up. So in October, we will be holding our meetup in conjunction with TensorFlow World. In November, we will be having it hosted by the DSP group. In December, it will be in conjunction with the ARM AIoT Dev Summit. And in January 2020, it will be hosted over at Lattice Semiconductor in San Jose. So these meetups, you'll see the notices on meetup.com or the announcements on LinkedIn. So please follow our announcements. So although our name is tinyML, we've been seeing a lot of growth. Our LinkedIn community crossed 500 members. Our Bay Area meetup group is almost 600 members when I checked a couple of hours ago. The Austin meetup, we just started I think less than a month ago. It's over 100 members already. As I mentioned, for the first time, we are trying YouTube live streaming. I hope it goes well. No, we'll try to improve our AV setup as we go forward. The idea is to have future meetup groups and viewers worldwide, either in locations like in Austin, where they all meet up at a specific location and follow along, or they can view it in the comfort of their own home. The next thing I'd like to ask is to kind of call to all of you. Would you like to present on a topic, anything ranging from a 5-minute tiny talk, as we call it, to a 60-minute full presentation? If you'd like to show your demos, like we have a few demos in the back here. If you'd like to sponsor a future tinyML meetup event, either by providing a venue to host it or providing refreshments like pizza, like we have today. Also, if you'd like to organize a meetup at your own location, I know we are typically in the South Bay Area, and for people who are further away in the Bay Area, it might be harder to come here all the time. So if there's any interest in hosting in other parts of California, as well as all over the world, we'd like to hear from you. A couple of last announcements. The tinyML Summit 2020 is happening in February, and the sponsorship opportunities are still available. And also the poster, the abstract submission deadline is on November 1st, 2019. And another event called SenseMac 2019 is happening in October in San Diego. You can go to sensemac.asu.edu. And the theme of this industry university meeting is also on tinyML. There will be people from academia, from industry, and there are poster sessions and presentations over there. So I highly recommend you take a look at that. I also want to thank Google, especially Daniel and Pete, for hosting, for the venue, and for the refreshments. And today's talks, we have Professor Boris Merman from Stanford, Venkat Rangan from tinyvision.ai, and Zach Shelby from Edge Impulse to give talks today. I will actually turn the mic over to Dan to introduce Professor Merman next. All right.
All right, so let's get our equipment switched over here, and we'll be ready to go. So Boris Merman is Professor of Electrical Engineering at Stanford University. He joined Stanford in 2004 after completing his PhD degree in electrical engineering at UC Berkeley in 2003. From 1994 to 1997, he was with Neutron Microelectronics, Germany, where he developed low power and smart power ASICs in automotive CMOS technology. Since 2004, he's worked as a consultant with numerous Silicon Valley companies. So are we,
thank you.
We're having some AV issues.
Where's my plug?
So just restart this. Perfect. So thank you very much, Boris.
Good. Thank you for the kind introduction. So I'm trying to get the pointer going here. So yes. So thanks for inviting me. Evgeny, contacted me months ago to give this talk, and he said, tinyML, as you know, this is very informal and so on. And so this is really the first time I'm giving an informal talk to about 150 people. It's an experiment. I honestly don't know how to do that, but I will give my best. Okay, maybe you can, throw a tomato every now and then to make it less formal, but we'll see. So this talk represents my perspective as a mixed signal designer. So I'm someone who actually designs circuits at the transistor level, and I have grown into this space, I would say 7-8 years ago. And the starting point was really when I talked to the self-driving car guys at our university, Andrew Ng, and these people. They built a lane detector at the time. So self-driving was starting up, and the first thing they need was some algorithm that was tracking lanes. And so they built something on a GPU, and the thing ran at about 100 watts. And that was not good. And so the car companies told them, come back when this is 5 watts. And so he started talking to me about, where does all this power go and so on, and the rest is history. And this is really what got me excited about this topic and think about lowering the power in machine learning. So my background is really in analog. Actually, some audience participation. So show of hands, who is working with a circuit schematic editor on a daily basis in their job? Not so many. Who works with a compiler? Software people. Okay, wow, I'm in the lion's cage. My stuff is not very programmable, sorry, but you will detect that throughout the presentation. But the focus is on figuring out what may be practical limits of energy. So you will hear the word joules a lot tonight. This is about joule. And so we'll see how that goes. So just real brief, the tinyML vision was already advertised. We want to do machine learning algorithms at the milliwatt level or below, and we want to stick these algorithms everywhere, including your toaster. And so what I'm going to focus on specifically here is not all possible machine learning algorithms. There's a lot of options. It's a big zoo. I want to focus here on what I would say is one of the best known workhorses. So deep convolutional neural nets. These are used everywhere. There's recurrent versions and so on. But this is the algorithm that's very mainstream. And so what I want to do is inspect how much energy we can sort of hope for when running a network like this. So for those who are not completely familiar, just as a rundown, a ConvNet consists of many layers. That's why it's called deep, and most of them are convolutional. They run filters across images from layer to layer to extract features, and in the end, actually, there's the final output class comes out, very coarsely speaking. So what has happened since 2012 was that people figured out the more data you feed into this and the larger you make these networks, the more powerful they become. And that is leading to models that maybe for the smaller algorithms could be about 100 kilobytes. And some of the biggest one, you're really talking about 100 megabytes or more worth of coefficients that are kind of contained in these networks. And what you then do with these weights is you compute. And obviously, you also have to move them around between memories and so on to store intermediate results. So when you look at even a moderate size neural network like this, you have to do about 1 billion arithmetic operations before you get one inference. And so one inference is basically, well, is this a cat or a dog that I'm looking at, right, for one frame that you're processing. So this is a lot of computation. And so if I now demand this to be significantly less than a milliwatt, say 0.1 milliwatt, I can do a very simple calculation on the bottom here. So I have a billion calculations. Maybe I want to do them every 10 milliseconds or so, and just to do some round numbers, video processing or something. I would need 1,000 teraops per second per watt in my fabric, right? It's that simple of a calculation. And this is really, in a way, the holy grail, right? So if I want tiny ML and very powerful ML, someone ought to ship me something like that, something that does this. And that's really what this talk is about. I want to do some back-of-the-envelope calculations with you to figure out if this is actually possible, right? How do we know? Is this possible or not? Let's try to figure this out tonight here, okay? So that's my goal. So luckily, a lot of people have done some work on this already, and so these charts are just getting populated, right? People are building processors that run these neural networks. This is a nice chart I stole from my friends at IMEC. Dave stole it from someone else, but it doesn't matter. And here's, you kind of see the variety of processors that people build. And obviously, when the x-axis is power here, on the left side, you really see this sort of few milliwatts to 1 milliwatt region that I would say is tinyML. So we have the power axis here, and then on the y-axis, we have peak performance. So this is tera operations per second. And then constant efficiencies are these contour lines here. And this is the 1,000 TOPS per watt line that I just advertised to you. And so you see very few processors actually achieve this kind of efficiency right now. And in fact, the ones that do are the ones that are actually not so great in other respects. They're very efficient, but they're crappy in other ways. And I will explain to you what that is. One of them is actually a chip done by my student, published last year. This chip is very efficient, but it has some problems. It actually uses 1-bit mixed signal arithmetic, so the accuracy is not so great. The chip is also not very programmable. So I'm going to show you a little bit how these two things actually stand at odds. So people across the fence, that care more about programmability and build real processors, not myself, they're more in this space, and they say, well, we got to use 8 or 16 bits, or maybe at least 4 bits, and the thing has to be very programmable. And then they actually end up being about 2 orders of magnitude less efficient. And so today I want to discuss a little bit where this comes from and whether we can actually move over. Can we move these guys in this direction and actually make them as efficient as this thing, have multi-bit computation, programmable, and so on. Everybody wants that. Everybody wants this zero power, super programmable device. Right? And so I'm going to highlight this contrast a little bit in terms of what actually pins us down here in these very nice processors, and how could we maybe move a little bit this way. All right, so I hope this sounds like a good plan. So what stands in the way of building these 1,000 TOPS processors? And we don't want to sacrifice any accuracy. We're greedy, and we want to program because we have all these software people in the room. Right? So the first thing I'm going to go through is what sets some of these asymptotes. Why is it? I mean, the people who designed these processors, they're no dummies, right? So if they end up at 10 TOPS per watt, which are actually a very good result, why is that? Why didn't they get 100? What are they bumping into? What is that ceiling? So we're going to calculate a few of those, and then I'm going to brainstorm a little bit about, well, because I'm an analog guy, I'll just sprinkle some analog stuff in there and see if the world gets better. Right? And then we can go back and have some more pizza maybe. All right, so first of all, we need to calibrate ourselves a little bit on metrics because this can be quite misleading, and I want to make sure that everyone in the community understands this. I learn a little bit about this every day, and so I'm going to try to give you my best view of it. So what is power? Power is some rate at which you do an operation times the energy that it takes to do that operation, and our operation is an inference. We want to figure out if something is a cat or a dog or something like this. And by the way, I didn't say it explicitly, but my entire talk is about inference. Training is yet another big problem that is beyond the scope of what I want to talk about. But so my operation of interest is inference. And really, while the rate is probably set by the application, maybe it's video, or maybe, I don't know, someone may want to take a shot every 10 seconds and classify that. That is probably set by the application. And so really what I care about is how much energy I dissipate per inference. Now, I can decompose that number, as shown on the right, into how many operations did I do per inference, and how much energy did each of these sub-operations take, right? And so what becomes very obvious then is if I want to do well in the metric that I care about, I have to minimize this product. So the second term in this product, energy per operation, is actually directly related to this TOPS per watt thing that I've been throwing around, because a picojoule per operation is the same as 1 tera operation per watt, right? It just depends on who you ask. Analog guys like to talk energy. Compute guys like to talk TOPS per watt. But it's actually the same thing, unit-wise. And so if you dissipate 1 picojoule per operation, that's like achieving 1 tera operation per second per watt. And so now, what's a little confusing, and this gets played out in the publication space a lot, is that you can actually build a fabric that has incredibly good TOPS per watt, but is a very awful machine learning processor because it requires a lot of useless operations or a lot of idle operations, or it doesn't deal well with sparsity of operations or something like this. So in other words, at the end of the day, when you evaluate the goodness of a processor, you actually have to look at both. You have to look at how clumsy is it at maybe wasting operations for inference, and how good is it at expending energy per operation. Now, the caveat about this talk is I will talk only about this because I assume that the former has been taken care of. I'm basically saying, let's assume you know what you're doing and you know how to use this fabric efficiently. And let's say you're not playing any games. So I'm only going to look at this raw performance metric. That anyway, is pretty mainstream in the compute community. But it's important to know that you can easily get fooled by people who just tell you some TOPS per watt and then they do some really inefficient processor with that. It's certainly possible. Here's actually one way to sort of get calibrated, right? So if all you did is build a NAND gate, so now, obviously it depends on the process and it depends on the process flavor. Is it low leakage? Is it high performance? How much energy does it take to toggle a NAND gate without too much wire on it and so on? 0.2 femtofarads or so. 0.2 femtojoules or so. So the inverse of that is 5,000 tops per watt. So if anyone tells you that they built a machine learning processor that has more than 5,000 tops per watt, they must be doing really, really magical, because they have just beat the NAND gate. And so I will show you a little bit later that at least my students claim that they think they can get 3,000 tops per watt from some fabric. And you can imagine then how many transistors and wire that can involve. It's basically a bit of nothing. Right? So this is just to calibrate yourself. So these numbers, they're kind of grounded in what we can do in integrated circuits and how small we can make features. And if you ever see anything larger than this, it's probably nonsense. By the way, this game gets exploited a lot in chip publications as well. You know, people build something slightly more complicated than a NAND gate, and then they call it a processor, and then they say it has, you know, I don't know, 800 tops per watt, and then they compare it to some GPU and say I'm 1,000 times better than a GPU. That's of course nonsense as well, because when you scale something up, it is very difficult to maintain the same efficiency and amortization of resources as in a small NAND gate. Right? So this is something you need to be very careful about and don't get fooled by. So jokes aside, since this NAND gate is so efficient, why don't I build a whole neural network out of NAND gates? I could do that, right? I mean, you learned that in your digital logic class. You can make anything with NAND gates. Right? Digital logic is easy. Just put a bunch of NAND gates there and you're done. How exactly? Well, there's a tool that does that. You just press a button, right? Sorry, guys. So could we do that? It doesn't look very good. So, you know, my student Danny is very inquisitive, and so he did one of these calculations in his thesis. Suppose you did this and you took not even a very large neural network, but let's say one with 1 billion connections, not necessarily even fully connected. This can be convolutional, but even in convolutional networks, we would have about 1 billion connections to make. And then you assume per connection you have one multiplier and one adder. And I'm even sweeping some of this other stuff under the rug. I'm assuming there's no memory. I'm also hard coding the weights between VDD and VSS. You know, that's completely bad, but let's say I did that. So then I can look at how big are these cells. So I can look at how big a multiplier is in terms of adders. I can look at how big an adder is in the modern technology in terms of lambda. This is sort of feature size over 2. And then you can find out that one of these multiply add units would be 133 square microns. That doesn't sound so bad, but when you multiply that out, it becomes 133,000 square millimeters. So that's a pretty ugly chip, right? This is kind of a chip like that. So you can't really do that. I wouldn't recommend that you try this at home. And so, you know, of course, you can improve on this, but you know, maybe you get an order of magnitude if you're really clever, but just forget. And so that's why we're not building neural networks like this. That's at least one of the reasons. That's why they look a little more sophisticated. They tend to look like this. So we need dense memory because, well, we need you know, maybe 100 megabytes of weight or something like this. And this most readily fits in some of the densest memory we have, which is DRAM. And then we somehow have to get these bits on chip, and we have to efficiently use them. So I will explain this a little bit later. What then follows is that we have this hierarchical memory architecture where the data gate basically gets pushed from memory to memory into a register file. So RF means register file, until you finally get into multiplying and adding and then writing back to memory and so on. And so this dance between compute and memory, this is a scheduling problem. You know, when and how do you compute what, and how do you reuse data, and how does the data flow? How do you network these things together? This is what, you know, people in the building next to mine work on 24/7. This is a really hard problem, and a lot of progress has been made in this. So if you have a model that's, you know, say bigger than a megabyte, I would say people will often go to DRAM, because otherwise the chip will be too big. Squeezing more than a megabyte of DRAM on a chip is hard. You can do it, but then the chip gets big, pretty big again. And so this is sort of the breakpoint for DRAM. So whether tinyML will actually need DRAM or not really depends on our friends that do model compression and stuff like this. So if we actually down the road find a way to compress some really high-performing algorithms into, say, less than a megabyte for a large variety of operations, maybe we don't even need DRAM. But the reality is that for many high-performing algorithms, you may actually still need DRAM nowadays. So with this architecture, it's really all about data movement, as I just said. How do you move data between memory and so on? And so, since this is an evening talk, I wanted to illustrate this a little bit. This is an aggressively scaled SRAM cell, and if I pretended that the x direction of this was kind of the length of a car, so it's really a fraction of a micron, but suppose that was 5 meters. Okay, why not, just to get a feel for this in the macro world? And then I look at an accelerator like Iris, and I know in an Iris accelerator, you have an SRAM buffer here, and then some of the bits, they have to travel 4 millimeters across that chip. Now, if the SRAM cell is the size of a car, that's like driving from Stanford to Tracy. That's about 60 miles. So I think now you see why is it significant to move data around on a chip. You wouldn't want to drive to Tracy for every bit that you want to process. This sounds awful, right? This is really, really bad. The good news is that there's data reuse, and we're going to go into that a little bit. But I just want to illustrate that data movement is a thing. It's something you need to think about. On the other hand, if you go into these processing arrays, inside the processing array, there's a little bit of register file. And if you want to go from the register file to the compute unit to the multiplier or the adder, that's a shorter trip, maybe 100 micron. And then again, scale to the car, that's from the Stanford Oval to the sports bar. So I prefer that trip, right? It's much shorter. It's just, it's a little more than a mile. And so that gives you a sense of distance and so on. I should also say, this is a pretty bumpy road inside the SRAM because there's a lot of capacitance here. There's all sorts of bit cells hanging here that make you dissipate more energy and so on. And we'll talk a little bit about that as well. All right, so let's put some numbers down, right? So for those who don't do that in their daily lives, how do we get a ballpark? It's kind of something that I would pin to my wall so that I can say something when an investor calls or something like this. These numbers, don't go to court with me on these numbers because they vary depending on technology and exact sizes and so on, but just ballpark. So if you wanted to move a bit out of a DRAM on the chip, it costs you about 10 picojoules. And this is because you have to go through a high-speed link and you're actually traveling pretty far in that DRAM already by itself. You have all this circuitry, right? Think about the drive from Tracy, the drive to Tracy, that went here. The DRAM is even further out. So that corresponds to 10 picojoules per bit. Once you're on chip and you're putting something from your first level memory here, so that this highest level cache, if you want to call it, these are often 100 kilobytes in the kind of processors that people publish now. It's about a picojoule per bit, so you're an order of magnitude down. Then when you go to the next level and you build a memory of 1 kilobyte, you're again an order of magnitude down, maybe a fraction of a picojoule. And then these register files, they're often only 100 bytes. Depends on who architects this stuff, but sometimes they're 100 bytes, and then you're looking at 10 femtojoules per bit. And so now again, for the computer architects, right, this is a really interesting optimization problem. How do you move this stuff around? Also considering that these are your typical multiplication energies, add energies, and if you want to go down a wire, it's about 200 femtojoules per wire. And so, right, a digital processor designer has all these numbers, and they run optimizations, and then they figure out a schedule and a data flow that makes the energy as low as possible. And this is a completely non-trivial problem, right? This is actually really hard. So what I want to do now is get some asymptotes. So for example, how much energy would you actually expect this DRAM interface to contribute, and what efficiency asymptote does it lead to? So the good news is that I will actually not bother the DRAM in every cycle. If every time I had to do a multiply and add, I had to bother the DRAM, you could forget tinyML until the end of time. There would be no way to do tinyML because that would be way too much energy. And the reason for this, the reason that we can actually do this and not bother the DRAM too much is because there are ample data reuse opportunities in convolutional neural networks. Let me just point out the simplest one. You can read this paper if you want to learn all of them. But in a convolutional neural network, you take a filter, maybe 3 by 3, and then you slide that across an image. Right? And you look at different locations for edges and things like that. So the trick is that you load this filter only once and then use it a few thousand times before you load a new filter. Right? And so that's data reuse at the filter level. And then there's other reuses you could do with input and output activations and so on, but this goes a little bit too much into the weeds. So what is a typical reuse factor for a convolutional neural network? Well, you can look at some examples like the Iris processor, done at MIT by Vivian Z. This network fetches about 15.4 megabytes for every 2.6 billion operations. So these are multiply adds. So for 2.6 billion multiply adds, she's fetching 15 megabytes from the DRAM. That's pretty good. So that's like a factor of 1,000 between these two. So there's sort of a 1,000x reuse. Every time you compute something, only every 1,000 times you need to go back to the DRAM. And so we can make a calculation based on this that basically says my asymptote on energy per operation, if I considered only DRAM, nothing else, what would it be? Well, weights times access energy per weight, and then that gets amortized by the number of operations I do with these weights. So for example, this is just a rounded example here. If I need to fetch 10 million weights to do 1 billion operations, and I expend 8 picojoules to fetch a byte, right? 80 to fetch a byte, 10 per bit, I'm at 800 femtojoules, which means 1.25 TOPS per watt. So it's good that we have reuse, and it gives us 1,000x in amortizing DRAM, but this doesn't look like it's going to revolutionize the planet. I asked for 1,000 TOPS per watt at the beginning of the talk. So the bad news here is that at the moment you stick DRAM into a system, it's actually very difficult to get beyond single-digit TOPS per watt. Very difficult. And that explains some of these processor papers that you saw in the beginning. If something is below a TOPS per watt, has a big DRAM hanging on the outside, gee, that's no surprise. Here's the algebra. Right? And some of the efficient ones actually do not have a DRAM. So this is a pretty important piece of understanding. So how do the other memory blocks work out? I could now do a lot of calculations, but I just want to show you a graphic because this actually becomes a lot less obvious how much reuse you have, because now it really depends on how you design your processor, how you do the data flow and schedule and so on. So this is done from one of our PhD students, Xuan. And here's just to see the optimizations that the computer architect does. She actually plays here with different register file sizes in the different layers. So these are different convolutional layers, and then come 2 fully connected layers at the end of the network. And you actually see here the arithmetic is actually barely visible here. And then there's DRAM access. There's actually more DRAM access in the fully connected layers. And this makes a lot of sense because the fully connected layers do not use sliding filters. They're actually fully connected. So you get hit much harder from the DRAM. But then how much exactly depends on what your compute architecture looks like. And one thing that stands out here very nicely, the size of the register file actually plays a big role. If you make a large register file versus a small register file, the problem with large register files is that you have a lot of capacitance hanging on each bit line. So you're actually dissipating a lot of energy every time you access this, and this is why these bars look so terrible. And one of her contributions for a PhD thesis was to figure out what the optimal register file size is. She figured out that 64 bytes is enough, and that makes much smaller capacitance. And you end up with a much more balanced energy profile in the memory architecture. Okay, so this is the kind of stuff that people do, and I'm not an expert in this at all, and my students are not working on this, but that's what a lot of digital architects do. So looks like these register files are important, so let's look at that a little bit more. So if I go into these tiny tiles that have a register file and a multiplier and an adder, that's actually what it looks like. So you have some ALU and then this register file, and so you have to fetch, operand A, operand B, and then you do a multiply, and then you have to write back the result and so on. So if you define a MAC operation done in this block and count that as 2 ops because it's a multiplication and an addition, that's how the signal processing guys do it, sorry for them. A multiply and an add is sort of the same thing. A digital circuit designer has a hard stop event when you say that, but for architects, it's okay, it's the same thing. If we just say that, then this is really the energy you're looking at. You have energy from the register file, from the multiplier, from the adder, and then some communication overhead, because you have to pass the data maybe to the next tile if you do some kind of sort of accumulation across the tiles and so on. So there's always a little bit of overhead, and if I add up these numbers, some of these you've actually seen. This is the memory access number. This is the multiplier. This is the adder I showed you earlier. This is a little bit of wire, and then divide by 2 because I do a multiply add. You get to 275 femtojoules. And then again, I take 1 over that. And it tells me that the ceiling now is 3.6 TOPS per watt. So if you tell me to design a processor with this processing element, it's going to be very difficult, again, to actually cross 10 TOPS per watt. And a lot of the culprit is sort of distributed. It's sort of all of the above matter. If you just cut out the compute, it's not good enough because it's sort of balanced. The register file is like a third, and then this is a third, and this is another third. So it's actually a really nasty problem. Nothing really sticks out. So this is where I come in, and some of my colleagues who say, okay, you can optimize these digital architects and so on, but if you want to cross these asymptotes, I just don't know how you guys are going to do it. So let's try something different. And so I obviously have done analog design for a very long time, and we've tried a few things here and there. And I just want to share with you what kind of my journey is through these explorations. And I will tell you about the good, the bad, and the ugly. Okay, so I'm going to admit what doesn't work so well and what tends to work. For those of you who are familiar with neuromorphic circuits and so on, I'm not going to talk about that. Basically, I'm going to talk about conventional circuits, conventional architecture that apply multiplies and adds. There's many other things you could do and play with, but I'm going to stick to that. So, that's not new. So you just have to be old enough to know that many people have tried these things. And in fact, it's almost embarrassing that my advisor, Bernard Boser, when he was at Bell Labs, he worked on this in 1990 and earlier. He was trying to build an analog neural network processor. And at that time, they're trying to do trivial things like, trivial at the time was not trivial, like classify handwritten digits for the post office and for the ATM machine and stuff like that. And so they thought if they built an analog processor, anyone would want it, but it didn't happen that way. Part of this is, I have to blame the architecture a little bit. This is old school circuit design with high voltages and class A for the analog guys. They know what this is. It's current steering. It's actually very inefficient. The feature sizes were very big. The circuits were ugly, the parasitics. It just didn't pick up. And by the way, the whole machine learning field went into a big winter, right? That also didn't help these circuit developments. And then we woke up again, in the 2010s. So with that, right, I also woke up and I said, let's reevaluate this again. Does it actually not make sense to analog or what? And so I wrote a little paper in 2015 or 2014, and we looked at this again and we said, is there really no way you can beat digital computing with analog computing. And so what this paper shows, and you can read a little bit about this, is that there is sort of a 10x opportunity that I see when you want to do multiply-add operations with analog circuits, specifically with switch capacitors, which is actually a very good thing for CMOS. This is what CMOS technology is good at, switches and capacitors. We've known this for decades now. If you compute with switches and capacitors, how good can you get? And so this comparison, I'll walk you through these three lines. This black line is analog efficiency maximized. You can't really build an analog circuit that has lower energy than this black line, or there's some black magic going on. You've got to change the Boltzmann constant to get beyond this black line, more or less. The red line is when you take caps and you switch them around and you do multiplications and additions. And with that comes some complexity and excess noise and things like that. And that's why, the complexity pushes you away from that limit. And it's parallel to that for very high resolution. So these decibels, this is signal to noise ratio. If you divide this by 6, roughly speaking, you have the number of bits. So this is 10 bits, right? And here at about 8 bits, 6 bits, and so on. But this is parallel for high resolutions. And it turns out the lower noise requirement you have, the smaller you can make the components and the energy storage elements in your circuit. And at some point, they become so small that you're limited by the process technology. You can't make a smaller cap anymore because they're already minimum size. And then this curve bends over, right? And it becomes a little bit more like a digital circuit, which is relatively flat in this space. Why is this digital curve so flat? It's because adding a bit is relatively cheap in digital. In analog, if you want 1 extra bit, you have to go 4x in energy if you're noise limited. In digital, if you add 1 bit to a 10-bit bus, it's 10% or something like that. So the trade-off is very different. That's why this is sort of a log-like and this is very steep. But here we're approaching the digital because I always tell my friends, if you design a really low fidelity analog circuit, that's called a digital circuit. Right? So the two ought to meet somewhere, right? Because everything is analog at the end of the day. So it turned out we saw this and we said, hey, there's 10x to be had. Let's build something and do that. Okay, so we worked very hard and we wanted to do this. And we had this idea of building, we knew people want to do Mac operations, multiply, add. So can we really show this 10x? So we set out to come up with an architecture, and we built this with very small transistors in advanced process, 1 femtofarad caps, and so on. We came up with a way to do multiplication in a completely passive way. We did charge sharing between multipliers to actually do accumulation also in a passive way. And then we said, well, now we have this analog output. We got to give this to the digital guys, so let's put an A to D converter there. Right, so that's sort of a digital in, digital out, but secret analog computation inside type block. And so how well did we do? Not so great. So this thing came out, and at the end of the day, built, measured everything, right? No, not simulation. No, really built, measured in the lab. And so it's about 104 femtojoules per operation. So this is sort of the multiply adds averaged out. And so, I'm also just barely scratching the 10 tops per watt with this thing. So this was not super successful. And so what happened? What happened is that our analog circuit was actually limited by its digital components. So we built this thing in a way that required way too many clock transitions and control logic operations. And that is eating up almost our entire energy budget. The energy that's consumed in the analog domain is this yellow sliver. And all of this other stuff was just all the control about these really small analog caps. And so this was a reminder, right? So you can't just think about the analog energy. You have to think about what is the whole infrastructure consuming as well. So to break this down again, this is sort of a nice cartoon here. So you saw this earlier. This is kind of the digital trade-off curve for energy versus precision. This is kind of a limit forgetting about process scaling. When you put process and dynamic energy in, you bend this curve. And then for our topology, we actually thought we could maybe get this after post-layout simulation. But then what was missing here, and that really put the nail on the coffin, you also had to add an ADC. And so our sort of multiply add is about the same as a digital multiply add. So we started out with something that looks really promising, but we made a few small mistakes. Well, I mean, we could have designed this thing probably a little bit better. And we hit the digital line again. So what this lesson tells you is that there's no margin. You know, if you start with something really good and you make one small mistake, you get wiped off the racetrack. It's actually a really, really tough thing to do to beat digital. So, you know, academics don't give up. So we continued. And we said, well, we learned something really important. You know, we got to cut out as much useless digital control signals as possible. We got to simplify the multipliers. We got to reduce the overhead. We got to reduce signal-independent switching activity. Exploit low activity factors of neural networks. There's actually not as much switching activity as you may think in a neural network. And so we came up with an architecture that kind of fits our fabric much better. And so at the time, we got very lucky because the neural network architecture folks came up with a way to build neural networks with just binary weights. So weights that are plus minus 1. And the contribution really was, how do you train such a beast? And they figured that out. And what this means is if you can build a network with 1 bit, your multipliers just become XNOR gates. And that's really cool because the multiplication is then efficient. And the only thing that remains as maybe as an efficiency ceiling is the addition. And this is where we then added the analog idea in. We then said we're going to make a lot of small caps, and we're going to do the addition by charge sharing with very, very small caps. So I'm going to show you what this looks like in more detail, but that was the idea. And this time we actually not only designed a small block, not just a small Mac unit, we took a little bit more time because I think everyone should do this nowadays. You better work toward something that at least looks like a processor. So this chip that we designed next, it actually takes image data in and it spits a label out, and everything else is on chip. And so the problem size that we picked was small enough so that we could put all memory on chip. So this chip actually has 328 kilobytes of SRAM on chip. So it's not a tiny, tiny chip. It's a little bit bigger because we have all this memory. But this cut out the DRAM access energy, right? And opened up the possibility of actually shooting up in the TOPS per watt. Right? Because if you don't cut out the DRAM, you have really, you're hitting your head against the ceiling. So I'm going to show you a little bit about what's going on in this network for those who are not familiar with. So we primarily designed this for the CFAR10 image set. So this is not the most difficult classification task. It's kind of medium level, you know. It's not completely trivial, but maybe medium complexity. You're telling apart, you know, ships from horses and dogs and things like that. So there's 10 classes. But you know, even a human gets this right only about 94%. So it's reasonably difficult, right? And that human is a PhD student at Stanford, so it's not so bad. Of course, you know, we do IC design, so we're the slow athlete in the stadium. The FPGA guys jumped on this first, and they said we're going to build binary nets on FPGAs. And so they had the first few papers on this architecture, and they built networks like this one. You see that here, you know, a few convolutional layers with 3x3 filters, and then 3 fully connected layers. You can see here that they had their implementation required 1.67 megabytes weight memory. And with my academic budget for taping out a chip, I already knew we can't do that. We couldn't fit this much memory on the chip. So we re-architected this topology and made it a little bit leaner, but sacrificed performance in the process. Right? I mean, in life, everything is a Pareto curve. Right? You want to be small and efficient, well, probably you're not going to be as accurate, and so on. Right? And so we took this trade-off into account. We made an architecture that strictly uses 2 by 2 by 256 filters. It's not good to use 2 by 2 filters. It's known that 3 by 3s tend to do better, but we could implement this better and the chip became smaller. We also cut out any extra fully connected layers that we think we didn't need, because that again is a big memory hog. And so we ended up with a 328K memory. And at the same time, so the contribution, I'll show you where that comes from, is we went from tens of millijoules per classification to 3.8 microjoules. And if you multiply that with the frame rate and so on, this is in the end, I'll show you the numbers. This is a sub-milliwatt processor. This is the data point that I had in the very beginning of my talk. So let's look at how we did this. So basically, these 2 by 2 by 256 filters, they must get multiplied and summed up against the input image patches. And so this is essentially the atomic operation that has to happen on this chip. You have 1024 bits that want to be multiplied by another 1024 bits. That happens with these XNORs. And then you have to create the sum. And if you were to do this digitally, it would be a big mess, actually, because you have to build an adder tree of some sort. But this is where the analog stuff comes in. It turns out doing this with analog by just sharing charge between 1,000 capacitors, this can be pretty efficient. And this is actually ultimately why this architecture works really well. So if you now took, I want to get back to the memory problem a little bit again. If you now took this atomic unit, as efficient as it may want to be, and now you build a processor around it, and you have your SRAM where there are filters, and then you have your SRAM that has the input data. If every time you had to bother the memory, fetching data from here, fetching data from here, you would completely drown again in memory energy. And so the secret again is that you have to enable some kind of reuse. And the reuse here is enabled using local storage. So for the weights, for instance, we fetch weights from the filter SRAM, and then in our architecture, we kept that here in local latches. And this is again the same story that I already told you. Once you fetch the filters, you're going to reuse the filters again and again because they're just moving across the image. Right? It's the same filter, it just stays there. And so you bother the SRAM only once, and then you're using this filter many, many hundred times. And so thereby you amortize the SRAM energy access. Similarly, we need to amortize the access energy of the input. How are we going to do that? I cannot really reuse the input so well. I mean, how would I do that with one element? Well, that you can do, for example, through parallelism. So I now do 64 neurons in parallel, and it turns out I have to do a lot of computations per input with different kernels. And so each neuron runs a different kernel. So every time I bother the memory again, I actually get a lot of computation done for that memory access. And that amortizes the weight memory. So I'm now down with weight and input activation access to 2.1 microjoules, ended up being a little bit, sort of roughly half of our implementation. If we didn't do this, it would be all memory energy. And so then, this completes to a processor, and it's a little bit of a shame to call it a processor because it's not super programmable. It's a little bit programmable. You have these 64 neurons, and there's a state machine, a controller. You can run different number of layers. You can reconfigure things a little bit, but it's not like you can write some C code and then hit compile and run it on this chip. That's not going to happen. So this is a little bit limited, and I'm going to get back to that disadvantage. But the idea here was to figure out how much efficiency can I tickle out, right? If I sort of do everything that I can and know and so on, and forget the software for a moment. So here's a look into this unit. This is for the analog guys in the room, right? This is this array of 1,000 caps with the multipliers. They charge share on a long wire. And then on this wire, we can also inject the biases. This is required in any neural network. You need biases. And it turns out here we also do offset calibration of this slicer that generates the output activation. So this actually can be tiled very nicely. So each unit looks like this. So this is a differential circuit in the end. So it's not one cap, per cell, it's 2 caps. And then we have this multiplier, and this is the local latch that creates the weight stationarity. And so, yeah, you see this is a fraction of a micron, 20 microns wide. And then we stack 1,000 of these in this direction, and then 64 of them in that direction, and call it a chip. That's basically what's going on here. And the end result is this. So let's look at that carefully. So the energy per classification in this was 3.8 microjoules. At this frame rate, this is 0.899, so 0.9 milliwatts. So this classifies as tinyML. And if you do the numbers, and I like to put 1 bit here because otherwise it's a little misleading. So this is 532 1-bit tops per watt. So I put the 1 bit because it's it's a 1-bit multiply and add. It's much easier than a 4-bit multiply add or an 8-bit multiply add. But nonetheless, this is not a horrible number, right? And you can kind of see, remember my NAND gate example in the beginning, that was 5,000 tops per watt. And you can kind of see we're sort of 10x below the NAND gate limit, which means there is not much inefficiency here. And there is not a whole lot you can cut out, especially not unless you make a very dramatic change in the architecture. And that's what I'm going to talk about toward the end. So then, of course, we are getting pressed by questions. Oh, okay, but if you did the same architecture fully digital, how good would it be? So we did another chip, and that one we made fully digital, and it was synthesized place and route. And this thing not only was much smaller, it was also designed much faster. Obviously, it was much smaller because in the middle of this chip we did this fine-grained analog design, and analog designers are scared to death. They leave large spaces, and when grad students do analog layout for the first time, you can throw a football through these layouts. It's really not the most compact thing in the world. But anyway, it's not a horrible outcome. But really, the thing that was kind of concerning at the end is that it turned out that, well, yes, okay. So if you actually just did a complete digital synthesis of this, you would be about a factor of 3 to 4 worse than this mixed signal thing. But if I actually had gone in and did my best in kind of hand-tuning digital logic, in this neuron array, and really optimizing the last little femtofarad, we actually tried that with hand layout, which is a fair comparison because we did hand layout here as well. Then this thing is actually within a factor of 2 between digital and analog. And so one of the take-homes is, even if I cut my neuron energy to 0, this blue thing, I still have all this baseline because of logic and memory that is there no matter what. So even if you give me an analog fabric that has 1,000,000 tops per watt, and then I put this logic and memory around it to talk to it, it's over. Right? Then I'm just as good as the digital guys. And this is something to keep in mind. You actually have to make sure that whatever you put around these things doesn't drag them down. And so really the natural progression for us was to say, we gotta do better, we gotta reinvent the wheel again. And so this is now the second time I'm trying to reinvent myself. This was not a huge failure. The first one was a little bit bigger. This is a little more graceful landing. But there is still something to be done here. And so what are the limitations here that I uncovered? Well, first of all, this thing is not programmable. I mean, everyone who knows software here knows that this thing is not going to fly in a product potentially. You could do CFAR10 with it. We also did keyword spotting. It works reasonably well if you give the spectrograms as the input. But the accuracy was no good because we run 1 bit. It's actually not so much the 1 bit, it's more the 2x2 filters that cost us more performance. And then the chip is large. And lastly, and this is the nail on the coffin, the energy advantage over hand optimized digital is not revolutionary. So if I was doing a company, right, and I have this thing and I consider time to market, I'm going to go digital. So what do I need? I need to cut out all this weight movement. I need to completely cut it out. It's bogging me down. So I want an even denser array. I want a much denser array, in fact. I don't want to move any of these weights around. That gives me this weird yellow bar and this extra logic. And then, yeah, I want to be enabled to move even less data. And so this leads to in-memory computing. And there's a lot of hype about this. And I want to explain to you a little bit why, and why this is actually potentially justified. So the general case for in-memory computing is this. And in fact, this sort of combines a little bit, or sort of resonates with what I've shown you as a circuit earlier anyway. But here's the thing. So consider a normal SRAM. It's called random access memory for a reason. You activate one word and you read out this word, and this word has to travel a bit line that in length corresponds to the height of this entire SRAM. That is really wasteful. This is why, remember in the beginning of the talk when I said, you know, a 1K SRAM is this much energy, a 10K is 10 times more, and so on. This is where that comes from. Random access means you have a lot of parasitics to traverse when you pull out a bit. Now, in-memory computing, the idea is actually to access all the words in parallel and at these intersections do a compute operation. Very much actually the way we did this in the mixed signal binary net, only much denser, in fact, at the density of memory itself. And if you put an ADC now here or a slicer or something at the column, that gets amortized across the number of columns, the same way it did in our mixed signal binary architecture. So I want a denser fabric, and I want to do compute at these intersections, and each row has to correspond to a computation, and all of these have to be exercised in parallel. So how do I do that? So this is a very logical progression. You just don't build a clumsy tile like this that we did. I mean, it is a little clumsy when you look at it in retrospect. You can actually get the same thing by building this around an SRAM cell. So here, this latch, well, this is just this cross-coupled inverter. And then you need an XNOR and so on. Well, you built this with a few transistors rather than actual logic gates. And this is the idea of in-memory compute. And so this particular paper was done by Naveen Verma's group. And Naveen and I, we worked together a lot. And in a way, I think he would admit it, that this design inspired their design. And it's just better. It's a better idea. It's much smaller. This is the area of that. F is feature size. And so you see the density goes way up. The energy here is not as low because they have a little bit of a problem with the reset here. But anyway, this is the right direction to go to get better and denser. So, you know, Naveen and his gang, have been working on this for a while. They can also do multi-bit with this. You know, this concept is not limited to single bit. You can actually distribute weights in multiple columns. You can shift your input data across these weights and then just accumulate in the columns. So there's a way to extend this to multi-bit. They not only did that, they also put together something that is almost a complete processor. And they put 4 of these compute memory tiles, 16, 4 by 4 of these compute memory tiles on the chip with ADCs on the column. This is a batch normalization circuit that you need for any neural network implementation. And they have some memory access control and so on. And so here you see a little bit about the architecture. One of the downsides of this processor is it doesn't have a whole lot of memory on chip, so it relies on the external DRAM. So when they report the efficiency of this, it's actually remarkable. So this is 150 to 300 TOPS per watt. This is for, I think, 8-bit compute, and then it goes to 300 for 1-bit compute. But this excludes the DRAM. And if you paid attention in my lecture today, you know why. It's not possible to do 300 TOPS per watt and access DRAM with a neural network. So they're really, really bogged down by the DRAM. So this is now one of these cases. So now either you're going to make this chip much bigger and you get all memory on chip and somehow eliminate the DRAM, or you will be stuck with the DRAM energy efficiency. So how would you go about getting more memory on chip? And this is really where my research comes in now. So to me, this SRAM, compute in memory, SRAM is from an academic perspective, a done deal. You know, the industry should run with it, implement it, sell it, and move on with it. I'm not going to do more research on that because the concept is proven. But what's interesting for me now is to get the next level of density, which will also lead to the next level of efficiency. So an SRAM, a compute in memory SRAM cell, turns out, is actually still very, very, very bulky when you compare it to an emerging memory cell such as RRAM. There's others like phase change memory and so on. You can pick your favorite one. But these are, if I trust the technology guys, approaching 12F squared. So these cells will be almost as dense as DRAM at some point. So it's sort of an order of magnitude smaller, more density than SRAM. And the cute thing about it, they're non-volatile. They don't leak. You could potentially do multiple bits per cell by programming different resistance levels in here. So these are essentially memristive cells, if you want to call them that. They're memristors. You can program a resistance level there, and then ideally it stays there. Well, obviously it drifts and so on, but that's a whole nother talk. But at least in principle, you now have a cell where you can, instead of adding charges, you can add currents, and so you get accumulation of currents. And the multiplications just happens by voltage. V equals I times R. Basically, that's where the multiplication comes from. And so this is not a new invention. Let me go to this first. Matrix multiplication with these resistive cells, you can make an array out of this, and you can get a highly parallel matrix vector multiplication out of this. Just like I just showed you in the charge domain, you now do this basically in the resistive current domain. So there's a lot to say about A to D and D to A conversion, and I'll do that in a moment. But what motivates me to look at this is really the sheer density. So here's an example. If I were to take our old binary net and yank that into a new process like this, here I'm assuming 25F squared, our entire memory would be less than a square millimeter. So this is amazing density. In fact, with this type of memory, moderate-sized chips, once this type of technology has scaled, you get 100 megabytes of memory on a chip for tinyML, a few square millimeters. And that is definitely great, right? So you have eliminated now this DRAM ceiling. So it's now all about, right? So remember, if my tile is very efficient and my energy is very low, and this is all very dense, very low capacitance, the only way I could ruin this then is by attaching inefficient circuitry at the periphery. And this is really where you have to watch things. So this is precisely what we are working on in my group right now. We're working on efficient digitization of these column-wise computations. And we're doing this in the voltage mode. This is sort of detailed for the analog guys. You could think about throwing transimpedance amplifiers here to sum the currents and so on. You can forget that. Forget 1,000 tops per watt if you want to build linear amplifiers that are low noise and stuff like this. All of this stuff has to be very lean and dynamic and no current unless there's actually an operation to be done, and so on. So we're studying these things, and I don't want to talk too much about it. Turns out the ADC can take about a picojoule. That picojoule has to be amortized over many, many rows, otherwise it will kill you. But what's cool about this architecture is that you can come up with a streaming processor that looks like this. We didn't invent this. This I guess been around for a long time. Where you have a very large compute memory array, and it's taking data from just a small SRAM cache, and it's dropping outputs into a small SRAM cache. And this cache has only to be large enough to keep a working set that keeps these input activations busy. So it's just a sub-volume of your filter. So it turns out these can be kilobytes, single-digit kilobytes, very small. So the access energy of this is almost nothing. And then all of the efficient multiply add happens here. And then you just repeat this and go through it. And I'm not the only guy dreaming about this. This is a paper from my friends in Zurich. So this is basically ResNet 2032 mapped on a 4x10 array of these tiles, and you actually can figure out what the residual connections where they have to go between these tiles. And this would be an amazing processor, right? That can basically all the weights are just mapped flat on this architecture, maybe 100 megabytes, and then you have these small caches, and you have a network that now connects these. So we did some experiments to see how efficient this can get. It's a small network, CFAR10. We're working with 2-bit weights and activations. And we have some models for how much energy goes into this, the ADCs, the femto, joule, and so on. And the pure fabric, so this does not include the SRAM, but just this compute layer would actually be running at 3.85 pops per watt. So this is 3,800 teraops per watt. And the reason for this is very simple. We have a few thousand of these rows that amortize the ADC, so that energy gets divided to a very small number. Each cell is very small. It just holds fractions of femtofarads of caps spatially per operation. But everything gets amortized by the sheer number of parallel operations. And that gets you to this number. Now, obviously, if you add these caches on the side and energy, you're going to get dragged down to maybe still sub 1,000 tops per watt, maybe 800 tops per watt. I would say this is a really good result, especially since this is way more scalable and way more extendable and potentially more programmable than our previous work. So the last point I want to make here really is that, for those who are not completely familiar with it, these ADCs, if this technology actually ends up winning in some way, these kinds of ADCs will actually be very important, because if that energy is too high, then it doesn't amortize well enough across these thousands of columns, then you're in trouble. And for those who are not working on this on a daily basis, 8-bit A to D conversion is about a picojoule. But if you now walk to your development team and say, no, actually, I want to do 16-bit for marketing reasons, you may as well not start that development, because there's no way. You've talked about a factor of 1,000 in energy to go from 8 to 16-bit, and this just has to do with thermal noise, bringing the thermal noise down. It's a very steep trade-off, as I showed earlier. And so this is just sort of one of these little nuggets. But the state of the art is not exactly where I projected it, because what I showed you is something we're designing now. This will be fabricated sometime next year. You will see this published in 2021 or something like that. So the publication of 2019 looks like this. People play with small RM arrays. They build small A to Ds here, maybe 3 bits. They're testing some circuits, and you're ending up at 24 tops per watt. And this number is low because they're not amortizing across enough rows and so on. So this thing becomes efficient when it gets bigger. Okay, but the potential is there, and the proof of concept is already there. Okay, I think I'm already over time, but I hope you found this somewhat interesting to hear about Joule all night. If you didn't get anything of what I said, remember that these CNN processors, they're limited by memory access and data movement. That's just what it is. And so whatever solution you have in mind, whether it's analog or digital or whatever, if you don't think about that, you're not thinking about the right thing. So the good thing about some of these analog fabrics is that they actually can change the way you think about data movement, and in fact can allow you to make the weights almost completely stationary, especially with emerging memory. And so now you just have to push around relatively small working sets between these dense compute memories, and I think this is a very interesting paradigm. Now, that paradigm still stands at odds a little bit with what the software guys want, because a very high degree of programmability would mean that I would somehow have to be able to change the number of tiles on the fly or something like this, or maybe change the number of bits, do 4 bits here and 16 bits there or something like this. This is going to be very, very difficult. And so my perspective is the following. It's not going to happen that you get the most efficient fabric that is highly programmable at the lowest cost with really high bit widths and so on. You're not going to get all of the above. And so I think we as a community have to work together to figure out what is the right compromise. Right? Is 4 bits enough? I don't know. I mean, maybe it is. Some people say it might. And once we know these things, and once this comes together and it gets sort of accepted by the community, I think we really have a chance to build killer processors that really run at a milliwatt. Because physically the potential is there, especially if you do everything right. And if you really know what you're doing and you amortize all your energies properly, sort of 5 tops per watt, 5,000 tops per watt is the limit. I'm not going to beat the NAND gate, I can tell you that. But a little bit below, we can probably come in. So thanks for your attention.
All right, thank you very much, Boris. And I'd like to see if anyone had any questions for Boris. All right, so one over here.
So this is a completely different technology, but I was wondering if you could say a few words about the asymptotic limits for optical computing as compared to these.
Oh, optical computing? I'm pretty clueless. The thing about optical computing is, I think it'll be determined by the optoelectrical interface. And yeah, then I don't know what that looks like, because you have to see how you arrange these things. I know there's a variety of companies working on optical compute, but they also, in order to amortize the OE interfaces and so on, you've got to do this with massive arrays. And so I think, to me, this is more of a data center thing than anything else. And so I think for tinyML, I think in my career, I'm not going to look at it. But I don't have good numbers for you, because I think optical compute is almost free, but then getting it into the domain you want is expensive.
Can you comment on the security vulnerabilities that you may have introduced or you may have eliminated with the architecture?
You mean with these compute tiles? That's an interesting question. I honestly haven't thought about this at all. I bet being so regular is not good for security, right? Especially if you freeze weights, if you make them stationary. I guess there could be an attack that tries to figure out what your weight matrix looks like or something like this. Whereas if I constantly keep moving my data around, this is a little more difficult. But I'm actually not very knowledgeable about that subject matter, so I honestly can't tell you. Yeah.
Can I noticed in the data you presented, you had a mix.
Can someone pass the microphone?
Oh, I'm sorry.
Yeah.
Thank you. Thank you, Professor Merman. I noticed in the data that you presented, you had a mix of 28 nanometers, some 65 nanometer, and I noticed one was 55 nanometer.
Yeah.
Can you comment on, can you kind of give me a rule of thumb which says, how much more efficient will it be as the geometry is reduced in size? Are we limited by KT over C noise or analog noise considerations?
You mean for the mixed signal fabric?
Yes.
Yeah, this is a good question. I mean, it always helps to scale a little bit, no matter what people say about analog. I mean, for this architecture, it definitely helps. But a lot of the stuff you see here, yeah, this is simply KT on C. There's sort of energy you need to put in to overcome matching and so on. I mean, if we redid this in 16, we'd probably cut the power in half.
In half?
Yeah.
From 28 to 60?
Our work was 28, yeah. So
Right.
to go to 16, probably we'd cut it in half. A lot of it is also wire loading and things like
Yes.
that. Yeah. Yeah.
Yeah, Winfried Wilger, IBM. A fascinating talk, wonderful, clear. If you look at a device at the edge of a network, it's not only the processor doing the AI, but the sensors, communication, and so on. How does the energy of all that stuff around it fit into the overall picture compared to this?
Mm-hmm. Yeah, this is a really, really good question. And in fact, we had a paper at the ISC this year that tries to talk a little bit about this. In fact, if you really want to build a tiny system that gets to these energy levels, suddenly the sensor will be much more power hungry. And not only the sensor, but actually the data movement from the sensor into your processor is a big deal. Because you also have to expend picojoules for each bit to go from, say, a camera chip to a processor. And so this is why we advocated something where you do feature extraction or maybe first layer processor in the sensor itself to get a first order compression, right, by doing some ML in the sensor itself. And so this is actually a theme, right? So not only in memory, but also in sensor machine learning, where you do a little bit of this in the sensor and you try to come up with kind of a bottlenecked connection between the two sides. I think this will have to happen if we want the entire chain to be efficient. Absolutely true, yeah. Yeah, oh yeah.
Analog circuits, especially low voltage ones, they tend to be quite sensitive to temperature fluctuations and also electromagnetic influence. How do you feel about it?
Electromagnetic influence.
Less for AMI, but more from temperature fluctuations.
Yeah, so this chip is not very temperature sensitive, and the reason is it's just switches and caps. So the switches turn on and off, and yeah, if you make them hot, there's a little bit leakage, but we're clocking that thing fast enough that it doesn't matter. So this circuit runs almost like a digital circuit.
And ADCs?
Okay, so the ADCs, they will be heavily calibrated to absorb PVT. I mean, this is something that we do nowadays, right? I mean, if you look at the SoC in your modem here, they do exactly the same thing. So they have to be calibrated. There has to be some stuff going on to compensate for these things. But we know how to do that, so I'm not making a big deal out of it.
All right, so unfortunately,
Okay.
in the interest of time, we're going to have to wrap up questions for now, but we'll still be able to ask some more questions at the end. So next up, we have our next speaker. I'd like to introduce Venkat Rangan. Give me a second to get the AV. Thank you very much, Boris. All right, so Venkat Rangan is the founder of tinyVision.ai, enabling embedded low-power vision with tightly integrated platforms. Prior to tinyVision.ai, Venkat was a director of engineering at Qualcomm. Thank you.
Thank you. Thank you to the organizers for having me here. It's quite an honor to speak here. So Mohammed mentioned something about having tinyML in a coffee pot, right? And I think I'd like to take you in a slightly different direction from what he did. He looked into circuits. But to me, one of the goals of tinyML is to actually put machine learning in every device around you, right? How can that be done, right? And that's what I'd like to go over. So if you think about computer vision and let's say the coffee pot, right? If the coffee pot guy wants to put computer vision into their device or tinyML into their device, the last thing on their mind is going to be, how does this technology work, right? They're worried about coffee pots selling the stuff, making money. So there's a huge gap between people making chips, sensors, and devices, and the end device makers. And the building hardware is actually really hard. Right? I think that's why it's called hardware. There's a lack of knowledge. Even within this room, there are people who know about different portions of ML and hardware and software and systems, but very few companies out there actually have all of that integrated in one place where they can build real solutions, end-to-end solutions that can meet really low power targets. Large companies like Amazon probably have that kind of expertise, right? There is also the trouble with the coffee pot guy. He's taking a huge risk, right? Think about it. He wants to put ML for whatever reason. He's going to have to prototype this, prove out there's a market, and then go into production. So it's a very long timeline. You cannot expect end users to go out and start learning about machine learning, figuring out sensors, figuring out platforms, it's just not going to happen. So in order for machine learning to really make it to the end devices, we need a slightly different approach. Add to it the fact that it takes time. Right? All of this machine learning, figuring it out, there's a huge learning curve. There are multiple learning curves here. There's embedded hardware, software, systems. Add to it the AI component, which is still developing, right? Nobody knows how this even works. So it's a very highly specialized, multidisciplinary field. And it's also very fast developing, right? So I hope I've motivated you enough that there has to be a different way. Now, this is not the first time that a new technology is being introduced into the marketplace. Processors have been introduced, connectivity. There's plenty of new things that have come in. And if you take the example of connectivity, right? Wi-Fi or WAN, any of these are extremely complex technologies, yet you use it today in your devices. 10 years ago, you had to staff up large teams for that. Similarly, processors. Today, if you want to put a processor in your device, all you do is go get a Raspberry Pi or an Arduino and play with it. Why does that work? Because interfaces have been cleanly defined. So you have clean mechanical interfaces, electrical interface, software interface. All of these are clearly defined to the point where you can buy a module from a vendor which integrates all the stuff, and then you build on top of it. So the coffee pot guy will, for example, be able to buy a device that puts all this together, and then they build on top of it. That's what we do in engineering, right? We build layers. So what I did is I went off and said, hey, this is an interesting problem to solve. And I put together this little board. I have some samples in the back if you want to come look at them. What it does is integrates a low power vision sensor, a low power FPGA, a microphone, and an IMU, and all of the surrounding stuff required for it. It appears for all intents and purposes like an SPI device. So you can talk to it as if it were just another device on your bus. You can push models to it, see what the inference came out. So the barrier to entry is very low in terms of there is a clean interface. It's connectorized, so you can plug it in. It's designed for volume. So the trouble with things like a lot of prototype stuff is you can buy all the reference hardware from different vendors, put it together, and then now suddenly you have a whole board design on your hands. And then you have to debug it, test it, integrate the software. I started from the point of view of, yes, we want to provide open hardware and open protocol, open APIs, but we also want a path to commercialization, that is volume. So this device has been designed for volume. It's open, so you're welcome to take a look at the GitHub page. And the schematics are there, there's mechanical drawings, all of that is up there. On the AI side of things, developing the whole AI core as well as the framework to drive it is quite a large undertaking. So I'm taking advantage of the lattice Sense AI framework. Going forward, though, at the same time, we have to think about what the end user wants. They want to solve a problem. They want the coffee pot to do its thing, right? How it's done is to be abstracted away at some point. So this is just the first incarnation of the device. Other things that I think TinyVision AI can do is I created this as a prototype to really go off and look at what people will do with it so that you can customize it later for specific applications, because I know this is not the right form factor for many of the things that people might use it for. You might want a different shape, you might want something else, right? Some other sensors on it. So those are all different things that we can do. So thank you very much.
So what kind of language do you use to program it? Is like Verilog, VHDL? What do you use to actually train or write in your models?
Could you clarify that, please?
Like if I have a model,
Yes.
should I re-implement it in the weights and everything in VHDL, Verilog to actually write to the FPGA, or how does it work?
So that would be a very, very high barrier to cross, right? The goal is to make it easy for you. My way, I would call myself successful if you bought this thing. In 5 minutes, you were able to get it up and running. Within a day, you're able to say, I wanted to do this face detection, whatever. Within a day, you're able to do it. That's not going to happen with Verilog. The way I've designed it is I have a layer around the AI core where you're allowed to push weights in, pull weights out, pull inferences out, and drive the code with a very simple API. There is a tool chain that Lattice has, which you can use, that takes a TensorFlow frozen file and converts it, it quantizes it and creates a binary image. So you can push that image in and out. So no, there would be hopefully no Verilog coding, unless you really wanted to go off and fiddle with it, in which case you are free to do so, right? Because after all, it's an FPGA, so that's a great thing about it. You can go change it if you want.
I was just wondering why the choice of FPGA and not Iris or any other kind of architecture?
So there were many reasons for it. The one is availability, right? I looked at it from the viewpoint of I want this device to be easy to manufacture, right? Which meant the chips have to be easily available at a reasonable cost. It doesn't make sense to buy something that's another like low volume production thing. It has to be high volume, it has to be proven, it has to have a reasonable tool chain. I mean, if it's built for production, you don't want to use something pre-production on it. So that was one of the main reasons. But that doesn't mean that I'm locked into one also, right? I mean, it's at that point of time, that's what made sense. There are other incarnations of this quite certain.
So just to ask again, so the chips are from Lattice, right? So you did the software in TensorFlow on GitHub, right? So the product of your company.
What is on GitHub is not the software, it is the...
And also the board.
It is the documentation, the interface to the board. The wrapper around the Lattice core, that is not yet on GitHub.
Oh, okay.
It's somewhere, it's still being worked on.
And also, what about performance metrics, like, tops per watts, and do you have like any numbers for efficiency and comparison?
I am certainly not anywhere near that number.
Is it below one?
This is, oh yes. So it is, to give you some idea, the imager is a QVGA, which is 320 by 240 monochrome global shutter, and running it a VGG8 type network. Lattice advertises about 7 frames per second. It's a little bit, so the whole board is consuming about somewhere around 8 milliwatts. It's in that range. I have actually, so there are other optimizations that can be done to push it up to maybe 30 frames a second at a similar similar power.
You have the number per classification like
I do not. The way I see this being used, frames per second is a very deceptive number in this sort of space because this is not intended to compete with the GPU. it is really designed so that it wakes up, does something, shuts down, right? So there is no frames per second in that. It's really what you asked is energy per inference. That is what should be used. And yeah, I don't have that number.
All right, thank you so much.
Thank you.
Thank you for all your questions. All right, so next up we have Zach Shelby. So Zach is an entrepreneur, investor, and technologist in the embedded space with a passion for tinyML and internet engineering. Zach is a former ARM VP, founder and CEO of the Microbit Foundation and Sensinode, active in several of his portfolio companies, and secretly working to bring ML to any embedded device. So thank you, Zach.
Thanks, Sam. Hi, everyone. I'm going to talk to you about a little journey that I'm on with my co-founder, who's another embedded software geek. And we had an aha moment about 2 years ago at ARM when we started to see a trend in compute efficiency that was starting to radically beat radio efficiency. This is a really important trade-off I'm going to talk about. It came up earlier when there was a question about the entire system. The other aha moment for me was when we started experimenting at ARM with open source frameworks for embedded developers. We said, wow, how can we make this stuff easy for an embedded developer? Because most ML toolkits are designed for data scientists. So we started working on an open source project called Microtensor. Really cool stuff, and we were amazed by the pickup we got from the community. They said, wow, we want to do this. We want to be ML people too, right? Not just those data scientists. And we thought, okay, we're on to something. So we worked on that project for 2 years. We brought it up, matured it. And just in May, we joined forces with the TensorFlow Light Micro team with Pete. And we talked about it at the last summit. Now, we got so excited about this stuff with my co-founder that we decided to leave ARM, our cushy corporate jobs, and go full in and help create the thing that we think is going to help developers in embedded with no ML experience really start to learn how to take on this technology that we're all talking about and deploy it in today's Cortex-M technology. Now, what's happened in this, what I call the compute versus transmit inflection point is really interesting. If you look at compute, and when I talk about compute, I'm talking about the entire chain from sensor, say 3-axis MEMS accelerometer, to a standard Cortex-M4. The amount of energy that we're now spending as the amount of data that we're processing increases, say you increase the sample rate of your accelerometers, it's increasing very slightly as the data increases. However, at the same time, radios have not improved with Moore's law, right? Radios are bound by physics. We get a little bit better with our analog transmission and reception circuitry. Feature size improves our efficiency of radios somewhat, but it does not improve with Moore's law. So what's happened now is that as the amount of data that you're processing and you want to transmit all that data to the cloud, that goes up very quickly. What's happened is that really, really quickly you hit this inflection point where it is now cheaper to leave your MEMS sensors and your Cortex-M4 on all the time running an ML workload than to send all that data to the cloud. And interestingly enough, we've gone into a mode in the industry where we're not only working with high bandwidth radios, say Bluetooth Low Energy, Wi-Fi, you're in the land, well, okay, right? It costs me a little bit more from a power perspective, but I could send this data to the cloud if I chose to, and there might be good reasons to do that. But interestingly, low power wide area network radios, say Sigfox, LoRaWAN, NB-IoT, you're down at the tens, maybe 100 kilobit per second level. And you're hitting your max transmit speed already before you hit your energy window. So some really interesting trade-offs that are happening. And I think this will fundamentally push a lot of people in the embedded industry towards ML versus just pushing everything to the cloud. So this is going to be interesting to watch. Now, I'm no longer a research scientist I was when I was younger. I'd love to find somebody in the research community who wants to study this more deeply on real hardware and different radios and find out what this trade-off is. So my CTO would surely be happy to work with you. But how did we get here? I'm an old school compute guy. I started coding on Commodore 64s here in the US. And I think it's important to understand how ML fits into the embedded compute space. And I talk about ML as the third wave of embedded compute. There's a reason for that. When we started out working with embedded systems, so microcontrollers back in the 80s, it was all about machine code, safety, control, right? Us developers, we're freaks about 1 byte of data here, 1 byte of data here. Oh, can we just make that a little bit more efficient? How many lines of assembler does it take, right, to do this? And so we built very simple software systems. We built an application. Oftentimes we controlled the hardware directly from our application. We might have had a few drivers, maybe something called a kernel, and that's it. This is the first wave of embedded compute that we went through. And in 2010, something pretty interesting happened. I was working in wireless systems and low power wireless protocols like 6LoWPAN, IPv6, over these embedded systems. And people got really interested in connecting devices. Well, what happens when you connect a device? Well, your software stack gets a heck of a lot more complicated. Security, right? Libraries, operating system, high-level scripted languages. And so we went into this world of connected secure devices, and it really pushed our software complexity to the point where it is now, right? It starts to be pretty mature and embedded, what we're giving developers. That's the second wave of embedded compute. And I think we're just hitting the maturity level of this wave, right? It's going to still go on, but we're not seeing a lot of new innovations. I would say that JavaScript and Python coming into embedded is the next thing that's happening. We're already seeing the beginnings of that. What we did with microbit was bring that to children in school already. So we're pretty sure if kids can learn JavaScript and Python and embedded, that the old school guys can too. And this is what got me excited enough to go start a company in this space, is that machine learning is another way of processing information. We use a lot of rule-based programming today to process, well, if vibration's over a certain threshold, then something's moving. If it's under a certain threshold, it's still. Machine learning gives us ways to match patterns in sensor data rather than write rules. It lets us train a device maybe for a specific customer's behavior rather than having the same firmware for every customer that does the same things. But machine learning won't replace the rest of the software stack. It's really important to understand how this fits in. This wave of compute will give us one more block in our embedded system that we have to deal with. So a lot of other stuff happening. Machine learning will let us match patterns and fundamentally train embedded devices to do things. I think this is going to be really exciting. This will push the embedded software space for the next decade. But I'm going to be the first guy here at a tinyML Summit, I think, that's going to talk about market size. Because I think this is really interesting, even as an embedded engineer. And there's a couple of reasons for that, right? If we want to think about how we give this technology to all developers, we really have to understand how many developers we're talking about. And I got a chance to get involved with developer work while at ARM, and it turns out there's about 10 million developers that work with devices right now. Some are back-end guys, some are back-end software, some are embedded, but they're working with a device chain to make these IoT solutions go to market. And they're working with about 30 billion microcontrollers that ship annually, every year to the market. So these people are designing serious numbers of devices. Now, when you break that down a little further, about 3.7 million of them are professional developers, some are hobbyists. And if you break that down even further, 1.5 million of those professional developers have said they are interested to learn more about ML in surveys, right, given to those developers. So I'd say we have about 1.5 million developers right now that are interested in tinyML. So there's for tinyML organization, there's your TAM, 1.5 million members is what we want to get to. I think that's really interesting, right? There's a real pool of people that want to learn more. At the same time, the other thing that's happening is that most sensor data is being thrown away. When I go and talk to corporate people, right? People working with these devices, their biggest problem is that they have these great sensors, right? MEMS sensors are amazing. Very low power, we can collect huge amounts of data, and then we throw it away. Because of power, right? Because of bandwidth, because of memory, compute limitations. And I believe ML can open that up. But it only is going to happen if we give the ML technology to the same embedded people that are here. We're not going to create 1.5 million data scientists that want to come work with devices in embedded C. That's just not going to happen, right? We have to bring the ML technology down to today's embedded developers. And at Edge Impulse, the startup that we're working on is exactly the mission that we're on. So I'm not going to talk much about this. I have a demo, so I'm going to be back in the back with a demo of this and show you what it means. But in practice, we're trying to provide tinyML as a service for the normal embedded developer, starting with real Cortex-M class devices, right at the sensor interface, collecting data sets with security, with labeling, generating models, and generating entire DSP processing chains. Because the thing to remember is that these systems, the neural network makes up maybe 20% of the whole software stack that we have to give the developer. The rest is anomaly detection using classical ML, feature extraction, signal processing, right? Security. There's all these other things we have to do to make this work. But neural networks are a really interesting part. And then finally, we have to go through an entire cycle of testing to ensure that we haven't broken anything last time we did this, and then generating the code that goes on the device. Our philosophy is open source, so we're really excited to work with TensorFlow Lite Micro, CodeGen Technologies, and other open source projects. So we're going to be part of the open source community. So please come and say hi. If you're on the live stream, we do have a developer preview sign up on our webpage, so you can ping us there, and we'll be happy to tell you more. Thank you.
All right, so any questions from the audience?
I think I want to sit down.
Yeah. All right, yeah, so we'll have demos at the back. So I guess, Robbie, what's our schedule for Tiny Talks?
We're running a little late. Is there anybody else? Anybody interested?
Yeah, so is anybody interested in doing a 1 or 2 minute talk?
I'd like to.
Okay, fantastic.
Right. Do you want me to come up there?
It's up to you. Yeah.
I'll come up there.
Thank you very much.
Thank you very much. Hey, good evening all. My name is Martin Mallinson. I've come down from Canada for this meeting, and it's been very worthwhile. I've learned a lot. I've learned a lot from Professor Merman. I've listened to the other presenters, and it's almost as though they set up exactly what I'm going to say. It's unbelievable. My company is called Silicon Intervention, and it solves the problem that the gentleman from IBM asked. And it solves the problem that Zach just pointed out, which is that the radio power and the compute power have had a crossing point. So what does this thing do? My background is, look at the grey hair. I've been doing analog design since the 70s. And I didn't understand anything about AI until some investor said, I'm not interested in that. Can you do AI? And I looked at it and found out I could do AI. I'm going to put AI with the sensor. I'm not going to do anything to help you guys plan how to do awesome digital stuff. I'm going to put an analog AI computer right next to the sensor. And I'm going to win. And why am I going to win? Because I have an analog compute fabric that has 2 killer aspects. When the analog signal stops moving, the analog computer consumes no current. That's just like digital CMOS. Digital CMOS beat wonderful ECL because when the signals stop, CMOS doesn't consume any current. That's the first aspect of the analog fabric I've got. And you can be sure I'm going to be following up with this gentleman to learn more about what he knows because his presentation was awesome. But the second aspect is this analog computer does not propagate the signal from the input to the output. I want you to imagine 11 layers of analog neural network. You apply voltages at the input, and we all know how to calculate how long it will take for the output to appear. Tektronix taught us that. They taught us that when we connect probes up to oscilloscopes, here's the rule you use. It's 1 over the square of the times. That's how it works. When you put digital gates together, 10 digital gates in a line has a delay of 10 gate delays. When you connect a probe up to an oscilloscope, the delay is less than the sum of the bandwidths of each individual thing. You can exploit that fact. You can make an analog computer where the noise margin changes. Everything that Professor Merman is telling you about, the power dissipated, how low can we go, is to do with the competition between the thermal noise limit and how much noise margin you need. Let's not have any noise margin. Let's turn it all off. Signals don't propagate in the network. Now let's turn it on. And suddenly the signals come to life at the output. Check it out in SPICE. You will find that the output appears faster than the signal can propagate from the input. Us analog guys know that. We've been using SPICE forever, and we've discovered there's a trick to get SPICE to converge. You actually simulate it from the power coming on. Well, it turns out you can make an analog computer like that. So the final thing is, I want to say that there's nothing special. It's standard CMOS. So if you'd like to know more about what I'm trying to do, I'm the guy with the grey hair and the suit. My name is Martin Mallinson. Come and talk to me. Thank you very much for listening.
Hey guys, my name is Jags Kandasamy, co-founder and CEO of Latent AI. Latent AI is a technology spin-out from SRI. How many of you still know SRI? So DARPA Tech developed. So our technology is about quantizing during training and compiling that down to run on hardware. Anyhow. So targeting edge again, tinyML, appropriate place here. We are hiring. We have an office in Princeton and here in Menlo Park. Anybody interested in the compile side and on the data science side, we're open. Thank you.
All right, anyone else? And if anyone's too shy to come up to the front as well, you can sit down while you're talking. So it's up to you.
Great, thanks. Hi, I'm Roland. I'm here with Taras, my co-founder. We run a startup called Plumerai. We're with 17 people based in London, Amsterdam, and Warsaw. And we very strongly believe that binarized neural networks, BNN, are the future of computer vision. But to do this, you need both new hardware and new software, new training software. So we are designing a custom ASIC, an ASIC customly designed for BNNs, BNN inference. And we've developed something called LARC, which is an open source training library for BNNs, for binarized neural networks. It's based on the TF-Keras interface. It helps researchers with doing better research on binarized neural networks. It helps you to train binarized neural networks. And it also has a lot of BNN models in there, a whole model zoo. Let's check it out, LARC with the Q. We're also doing a lot of research on binarized neural networks ourselves. We'll be presenting a paper on a custom optimizer for BNNs at NeurIPS in December. And we would love to talk with more people interested in deploying efficient computer vision or general people interested in binarized neural networks.
Thank you very much. All right, do we have any more volunteers? Any last people? It doesn't look like it. Okay, so I guess that's it in terms of our formal programming this evening, and thank you so much for being here. And we have a while to hang out and see some demos and chat to each other, and I definitely encourage you to do so. I'd like to also thank my colleagues from Google for helping out today, and also Rami for helping this event take place. And yeah, I'll talk to you all on the floor. Thank you very much.